Have you ever wondered what's really going on inside a molecule? What makes them do what they do? Well, today we're pulling back the curtain on a secret force, a constant, invisible tug of war that basically directs how molecules behave. All right, let's jump right in with a bit of a mystery. Look at these two molecules. On the surface, they look almost identical, right? You've got chloroacetic acid and regular acetic acid. But here's the crazy part. One is nearly 100 times stronger than the other. Why? To figure this out, we're going to have to become electronic detectives. So the biggest clue we have to solving this chemical whodunit is something called the inductive effect. And honestly, the best way to picture it is as a literal tug of war for electrons that's happening inside the molecule, 24/7. Okay, so what is it officially? The inductive effect is a permanent dipole. That just means there's a constant separation of positive and negative charge. And it all happens because of unequal sharing of electrons in a bond. It all boils down to electronegativity. Some atoms are just way greedier for electrons than others. Now, this slide points out two things that are absolutely critical to remember. First, this whole tug of war happens through the sigma bonds, those single bonds that are like the backbone of the molecule. And second, and this is the big one, it's permanent. This isn't something that happens only when another chemical shows up. It's just part of the molecule's basic nature. Now, like any good detective, you gotta know the rules of the game. This secret force doesn't just do whatever it wants. It follows some very specific principles. So let's lay them out. Okay, this table right here does a fantastic job of showing you exactly what makes the inductive effect so special. Let's put it side by side with another effect, the electromeric effect. Just look at the differences. The inductive effect is permanent. It works through single sigma bonds, and it only creates these partial charges. The other guy? It's temporary, needs a trigger, and involves pi bonds. The most important thing to get here is that the inductive effect is always on. All right, here's the next rule of the game, and it's super intuitive. Think about a magnet. The closer you get, the stronger that pull feels, right? And as you move away, it gets weaker and weaker. The inductive effect is exactly the same. It's powerful up close, but its influence fades the further you get down a chain of atoms. And you know what? We can put a number on that. This distance decay is so predictable that once you get past the third carbon atom in a chain, the effect is pretty much gone. It's so weak at that point, we can basically ignore it. The pull just doesn't have that kind of reach. Okay, so if we have a tug of war, we need to know who's on each side of the rope, right? So let's bring in our suspects. In chemistry, we've got two main types of groups, those that pull electrons and those that push them. First up, we've got the electron thieves. These guys have what we call a negative inductive effect, or just -I for short. They are super electronegative, so they yank electron density away from the carbon chain they're attached to. You're looking at things like halogens, fluorine, chlorine, or groups like the nitro group. And then on the other team, you've got the electron donors. These groups have a positive inductive effect, or +I. They're the generous ones. They actually push their electron density towards the rest of the molecule. And the classic examples here are all your alkyl groups, like a simple methyl group or a bigger ethyl group. Okay, our detective toolkit is officially loaded. We've got the rules, we've got the suspects, the pushers, and the pullers. Let's go back and crack these cases wide open. So let's go all the way back to that first mystery. Why is chloroacetic acid so much stronger? Well, now it's simple. Step one, that chlorine atom is a major electron thief. It's got a strong -I effect. Step two, it pulls all that electron density towards itself away from the other end of the molecule. Step three, this is key. When the acid loses its proton, that pull from the chlorine helps spread out and stabilize the negative charge left behind. And step four, a more stable product means the reaction happens more easily, so the acid is stronger. Bam! Case closed. Pretty cool, right? But the same logic doesn't just apply to acids. For our second case, let's look at the mystery of carbocation stability. That's just a fancy way of talking about positively charged carbon atoms and why some are way more stable than others. This is where those electron donors, the +I groups, really get to shine. A carbocation has a positive charge, which means it's electron deficient. It wants electrons. So what happens when you attach electron-donating alkyl groups to it? They push electron density toward that positive center, helping to spread out the charge and make it much more stable. That's why a tertiary carbocation with 3 of these donating groups is way more stable than a primary one, which only has 1. It's all about sharing the burden. So, we've solved a couple of specific mysteries: the strong acid, the stable carbocation. But what's the big picture here? What's the real big reveal about this effect? This is it. This is the whole ballgame. By creating these permanent zones of partial positive and partial negative charge all over a molecule, the inductive effect basically creates a chemical roadmap. It tells other molecules where the electron-rich spots are and where the electron-poor spots are. It sets the stage and directs exactly where a reaction is going to happen. And that's why this is such a game changer. It's not just about memorizing facts. It's about prediction. If you understand the inductive effect, you can look at a molecule you've never seen before and make a really good guess about how it's going to behave. It really is like the silent director behind the scenes of a chemical reaction. So now that you're in on the secret, now that you know about this molecular tug of war, it really makes you think, doesn't it? What other chemical mysteries out there could be solved by understanding who's pushing and who's pulling? Something to chew on. Thanks for joining me on this one.